My name is Asad Bhatti, and right now I am going to prove the De Moivre's theorem using mathematical induction. Now, De Moivre's theorem says that if there is a polar form of a complex number, now as we know already that the polar form of any complex number, let's z equals x plus iota y, its polar form is going to be z equals to r cos theta plus iota sine theta. Okay, and if mod of r equals 1, we're gonna have z equals to cos theta plus iota sine theta. This is our polar form of a complex number when the mod of r is equals to 1. So the De Moivre's theorem says that if we raise the power of z by any number n, okay, any number n, I will raise the power by n. So this implies the power will be raised on the right hand side as well, like this. And de Moivre's theorem says that this power, if the function inside the bracket is cos theta plus iota sine theta, not minus, not multiply, just this cos theta plus iota sine theta, real part plus imaginary part of trigonometry. If this is inside the power of n, then we have cos n times theta plus iota sine n times theta. As you can see that the power of all of this is multiplied inside the angles of these trigonometric identities. So we are going to prove this. Now, let's suppose that this k is this isn't k. This is in terms of n. We have n over here, okay, like this. Let's suppose that this is our De Moivre's theorem. So we will prove by mathematical induction. Now, mathematical induction, as we already know, it has three steps. The first step is that we set n equals some random number, okay, some random um, natural number. Okay, since n belongs to the set of natural numbers, so we can set any, okay. We have to see if it really holds true for any number. So we will check for n equals 0, okay. So it means z raised to the power 0 equals cos theta plus iota sine theta whole raised to the power 0. And any number, it's going to produce some number, and any number raised to the power 0 equals 1. And we can write this as cos of 0 plus iota sine 0. Why can we write like this? Because cos of 0 gives us 1, sine of 0 gives us 0. So 1 plus 0 equals 1. So this holds true for n equals 0. We can also check for n equals 1. We can also check for n equals 1. Okay. Now z raised to the power 1 equals cos theta plus iota sine theta whole raised to the power 1. This implies z raised to the power 1 equals cos of 1 times theta plus iota sine 1 times theta. It's also true for this, right? I mean theta, we can write this as 1 times theta. So the second step of mathematical induction is, now that we have checked for some natural number, we are going to suppose that the result will hold true for n equals to k. We just checked that if n, we just checked that result held true for any n, for all n belongs to the set of natural numbers, right? Now we are going to suppose that n equals to k. It could be any number. Suppose n equals to k. Using step 1, this should be true. So we can write zk equals cos k theta plus iota sine k theta equals cos theta plus iota sine theta whole raised to the power k. We suppose that this is true. We name this as equation number 1. Step 3, now we have to show that result holds true for n equals k plus 1. Okay, now if we add 1, what's gonna happen? We have therefore set n equals k plus 1. So z raised to the power k plus 1 is equals to cos theta plus iota sine theta whole raised to the power k plus 1. Now what happens when one base has a sum of powers? The bases are same and and hence the powers multiply. So we can write this as cos theta plus iota sine theta whole raised to the power k times cos theta plus iota sine theta. We shouldn't have a problem with this, right? Like same bases, the powers is gonna add up. So if we go upwards, we're gonna have the same function right here, cos theta plus iota sine theta, k plus 1. We have this. Now using our supposition in equation 1. Now in equation 1, we suppose that cos theta plus iota sine theta whole raised to the power k, the result holds true for that. The De Morgan's rule holds true for n equals to k. We suppose that it's true. So we're gonna write this as cos k theta plus iota sine k theta times cos theta plus iota sine theta. And then we multiply the brackets. Every number is to be multiplied by every number. So we have cos k theta cos theta plus cos k theta iota sine theta plus iota sine k theta cos theta plus iota iota. This is an iota over here. Iota iota times iota equals -1. So we're having negative sine k theta times sine theta. So we're going to rearrange it as real parts and imaginary parts. Cos k theta cos theta minus sine k theta sine theta plus iota cos k theta sine theta plus sine k theta cos theta. Okay, now we have two formulas over here that says cos alpha cos beta minus sine alpha sine beta. This gives us cos alpha plus beta. When a minus sign exists over here, this is a plus, and when there's a plus over here, this should be a minus. It's a pretty weird notebook over here. And also we know a formula for sine. Sine alpha cos beta plus cos alpha sine beta. This gives us sine alpha plus beta, right? So we have cos alpha cos beta sine alpha sine beta. So we're gonna have cos alpha plus beta. Cos alpha plus beta plus iota. I don't need a bracket anymore. Cos alpha sine beta plus sine alpha cos beta. We can write this as sine of alpha plus beta. Here we are. We can also write this as cos, we can take theta common from them, k plus 1 plus iota sine theta k plus 1. And if we rearrange this, we have cos k plus 1 times theta plus iota sine k plus 1 times theta. And the other side of our equation was z raised to the power k plus 1, or equals cos theta plus iota sine theta whole raised to the power k plus 1. So we can write this as, therefore, cos theta plus iota sine theta whole raised to the power k plus 1 equals cos k plus 1 times theta plus iota sine k plus 1 times theta. This is it. This is our proof that if for k belong to, for all k belongs to the group of natural numbers. This is our proof right here. Using this, we can also write that cos theta plus iota sine theta raised to the power n equal. I mean, this implies that cos n theta plus iota sine n theta. But we do not know that if these are positive numbers or negative numbers. Let's suppose that all of what we did right now, was for the positive numbers. We can also check for negative numbers. Now, by using mathematical induction, we just check that if that for all the positive numbers, it's true. For negative numbers, we have an easier method. Let n equals minus m. Let n equals minus m. We can say that m is a positive number times minus 1. So minus m should be lesser than 0. So it's a negative number. I'm going to write next here. Therefore, cos theta plus iota sine theta whole raised to the power m minus m, sorry, minus m. Now, this is equals to cos theta plus iota sine theta. Now, as you know that we can write this minus m as minus 1 times n, m. Now, when does the power multiply itself? As we know that different bases, when they are being multiplied and they have different powers, what happens? Their powers add up. But what happens when a number is raised to a power and that whole number, that entire thing is raised by another power? Then we can write a equals b times c, right? So what's happening, that if the two powers are multiplying with each other, how are they being multiplied with each other? When the base is being risen to a power and the whole thing is further being risen to another power. See what I mean? Now, okay, there's a bracket over here. So we can say that cos theta plus iota sine theta raised to the power m whole raised to the power minus 1. We can write this as this, right? The powers are being multiplied. That means that minus 1, and since commutative law exists in minus 1 and m, so we can write m into minus 1 or m times minus 1 or whatever, minus 1 times m. So this is equals to minus 1 over cos theta plus iota sine theta raised to the power m. How did I do that? What happens when anything has a negative exponent? That thing goes to the denominator, or when it's in the denominator, it goes to the numerator. It's the basic rule of indices. Now we proved now m over here, m itself is a positive number, right? M itself is a positive number. It is being multiplied by a negative number. So we can say that minus m is a negative number, right? But here m is a positive number, and for positive numbers we already proved that De Moivre's theorem holds, so we can simply use De Moivre's theorem over here, right? If you didn't understand, we set n equals to minus m. This means minus 1 times m. That means that if m was a negative number, if m was a negative number, what would happen? Minus m minus 1 equals a positive number, right? But m is a positive number. It's being multiplied by a negative number. So the whole thing minus m is a negative number. So we have to show we are actually showing for if n is a negative number and n equals minus times a positive number. Okay. So and for the positive numbers the result holds. We just proved it. So we can write this as cos m times theta plus iota sine m times theta whole raised to the power minus 1, right? In fact, we can also look over here. Now there is a denominator in, there is an iota in the denominator, right? Now just in fact ignore this step right here. There's an iota in the denominator. How can we remove iota from denominator? We rationalize. And what is meant by rationalizing? We multiply and divide by the conjugate of the denominator. Now, our denominator is cos m times theta plus iota sine m times theta. So its conjugate will be cos m times theta minus iota sine m times theta, right? So we can say, therefore, 1 over cos m copies of theta plus iota sine m copies of theta times cos m times theta minus iota sine m times theta over cos m times theta minus iota sine m times theta. And we can do that because it all cancels out, it doesn't make any difference. So in the numerator we have cos m theta minus iota sine m theta, and on the denominator we have cos m theta plus iota sine m theta. We can just put these under brackets so it's clear. And cos m theta minus iota sine m theta. So it is a plus iota times b, a minus iota times b. And as we know that it gives us a square minus iota square b square. And iota square equals minus 1. So minus 1 b square. So we have a square plus b square. It's an identity. You can basically learn this by heart. Remember this by heart. So a plus b plus a plus iota b, a minus iota b. gives us a square plus b square. So cos square m theta plus sine square m theta. Now there's no iota over here, so there will not be an iota over here. Now iota has been removed. Now we know that there's an identity cos square alpha plus iota sine plus sine square alpha that gives us 1 whatever if the angles are same. Now the angles are same m theta, so we can write all of this as 1. So cos m theta minus iota sine m theta. We can write this as cos m theta minus iota sine m theta. There is just one problem. This minus should be inside, right? Now I'm going to ask you a question. What happens when the angle inside the cos is a negative number? Cos absorbs that. It absorbs the minus sign. But what happens when the sine of an angle is negative? Sine pushes it out, right? So if the angle of a sine is negative, that means sine of that angle is a negative. But if the cos of an angle is negative, then the cos should be positive, right? Now we're going to go the other way around. If cos of an angle is positive, that means cos of the negative of the same angle should be positive, right? That means cos of the negative of that angle should also be positive, should result in the same thing. And if the sine of an angle is negative, right? That means that the sine of the negative of that angle is positive, right? Oh, by the way, I forgot. So plus iota sine minus m theta, right? And what did we suppose the beginning of all this negative number thing? We said n equals minus m. So we're just going to replace minus m with n. So we have cos n theta plus iota sine n theta. That means that if n is a negative number, this implies that the rule still holds true for it. So this was your proof of De Moivre's theorem for all n belongs to the group of natural numbers. Now there are some definitions that say it belongs in the group of integers and not natural numbers. Well, that's same thing practically. Thank you very much.